There, officially starting recording. So, hi, folks. Thanks for coming back. I appreciate it. Happy Thursday. So, we got some things happening next week. Your first formative assessments is available. That is under quizzes in Icon, although it's not really a quiz. The deal is answer the questions as best you can. If the answer is, I'm sorry, I have no idea what you're talking about, can we go over this again? That is a perfectly fine answer. And you get your 3 points for doing it. And Erica and Vladimir are going to take turns leading those we've decided. They're going to do the same thing you guys decided. So I think Vladimir's up first on that one.
Yep.
That sounds right? Okay. Next Thursday, we are being kicked out of this classroom. So all of us will convene on Zoom instead.
It's an emergency.
I think it's just a coincidence that it's on that, but someone's having some kind of exam in this room, and they kick us out for that. Nothing due the next week. And so then homework 1 will be your next task. I hope to have that up probably by this day or so. So I try to put them up about 10 days in advance if I can. And the TAs will have done them already or worked their way through most of it. That way they're ready to help you regardless of which software package you're using, right? Yep, okay, excellent. Any questions about that? So whenever I release an assignment or a formative assessment for you to do, I will send you an email about it. That way you know that you don't have to watch for it. Let's talk about what we learned on Tuesday. So we can stare at the beach instead. That's a nicer view. Tell me what you remember from last time. Letters, abbreviations, symbols, gestures.
We did a re-go over of our clusters in various areas of our different TAOs.
Yeah, the hierarchical way of writing
Yes.
multi-level models.
We did that.
Yeah, so let's do a review, yeah. Suggestion?
I was going to say something.
Please say something.
We talked about ICC.
Yeah, that's where I was about to head.
Okay, cool.
How many kinds of ICC did we talk about?
2.
2, yes. So what's the first one?
ICC 1,
Mhm.
which is how much of the variance is accounted for by group differences, or by the...
Cluster differences or group differences,
Yeah.
take your pick. I'm using the word cluster because sometimes groups are predictors in that sense. And would you say explained by? Because you said accounted for, which is sort of in the middle of the semantic continuum.
Yes.
You would?
I would say, I feel like what I'd accounted for is kind of what I would say, but yeah. I don't know if they're different.
It's a thing, it's a philosophy that I'm trying to hone in. So it's like, yes, if you have an ICC of 0.3, then 30% of the information in your outcome variable has to do with which cluster someone is from. 30% is due to cluster mean differences. Due to, right, or attributable to, or accounted for by, all kind of sound like the same thing. But to me, it's different conceptually than the idea of explained variance in an R-square sense. Because we don't know why the clusters differ from each other. So it's just that we've isolated that as a separate kind of error that's differentiable from individual level error in terms of unexplained variance. So I think that's, you've identified an opportunity to explore cluster differences, and having an ICC that is greater than 0 is a logical prerequisite. Good. What else were you going to say?
So you're saying it's not
Yeah.
explained by, it's
I would not.
attributed to?
I would. But people will differ. So there are different versions of R-squares that are known as conditional versus marginal. And the conditional family counts random effect variances as explained. I just think it's a tricky point because when you first fit a single level model, you have all the variability in your residual. No one would say that you have an R-square of 100%. But if you pull some of that variability out of the level 1 residual, put it into the level 2 random intercept, then you could say, oh, my R-square is 30%. It's like, how did that happen? You just pulled the variance out. You didn't put in information that would say why it's there. So that's what I would say, is that it's not explained by in that sense, but you can say due to, accounted for, attributable, something along those lines. It says this is a reason, but we don't have any more details. Okay, ICC 2. What's that one? Should we look at that?
The reliability.
Yeah, people called out the reliability of the cluster means. It's a little tricky though because reliability is a function of the amount of cluster mean differences in the first place. So if your clusters don't vary that much from each other, like logically you're not going to have that high reliability unless you have like 100 people per cluster or something. Because it's a function of the size of the random intercept variance as well as the number of people per cluster. And if you wanted to increase reliability, do you want more people or less people? More people. Yeah, same idea. If you want to increase the reliability of a test, what kind of items do you need? More. More is better. But it can't compensate for a lack of cluster differences as a signal in the first place. So reliability is a tricky concept in these, but that is what people call it, ACC2. Let's go over notation. What are we now using for fixed effects in the hierarchical notation scheme? What symbol?
Gamma, right?
Yeah,
Yeah.
this is where gestures come in handy, right? I would also accept Y-looking thing. Depending on your font, it looks like Y sometimes, to the point where I've had students like write Y equals Y sub-zero, and I'm like, oh, no, that's a different letter. But it's a gamma. I pick notation based on what I can reasonably draw with a marker or a chalk. That's why. Snyders and Boskers use gamma, and they also use something that looks like U, I think, if it's not exactly a capital U. Does anyone know off the top of their heads? My book's upstairs. In the Snyders and Bosker book, what do they use for level 2? You have it. Yeah, you open it up and let us know in about 3 minutes or so. But I use U for level 2 random effects. What are we going to use for level 1 residuals? What letter?
Sigma.
That's the variance. Yep, so you're right. The variance of the level 1 residuals is going to be sigma squared. But in the individual values, what letter? For level 1. E? That's what I use. It's either going to be E or R, depending on what textbook you're in. That's a pretty universal choice for that one. Level 2 random effects can be all kinds of things. U is one option. I've seen so many variations of that. You just kind of have to look at it contextually. In a level 1 equation, what are the subscripts of the variables in a level 1 equation? What are we using this semester? PC for person and cluster. And order matters because the P spot is going to index which term in the level 1 equation we're talking about. And then the C spot is going to index which term in the level 2 equation for that level 1 term we're talking about. So it creates sort of this like row column kind of thing where you have one dimension at level 1 and one dimension at level 2. Good. What do they use? Did you find out?
My Kindle is needing to.
Oh, technical difficulties for you too?
No, it's just updating and stuff.
Of course it is. All right, well, you get back to it. I'm just trying to make sure that we all have a common system of notation that we know what's up, but it's always going to be author specific. It's always going to be contextual. So you'll see variations of this. What's this letter called for the variance of the U's? Tau. Yep. Yep, tau squared in that case. So it's the variance of the U's of the sub-zero. So I always put specifically what it is the variance of as a subscript, U sub-zero in this case. And then in the level 2 equation, should anything have a PC in the level 2 equation? Nope, because they're not people things, they're cluster things. So the variables at level 2 are only going to have a C subscript per cluster. All right, how are we doing so far? Okay, so if I told you ICC1 was 0.15, what's that mean?
15%, the variance can be attributed to cluster.
Yep, 15% of the total variance is attributable to which cluster you're in. Tell me about it as a correlation. Because it says inter-class correlation, right? So that's fair.
Mhm.
It's got to be a correlation of some kind. related to the idea of dependency as correlation? Okay, TAs. Erica? Yep, so the idea of that people from the same cluster are likely to have correlated residuals, that's dependency. So the intraclass correlation tells you the expected amount of correlation of people from the same cluster. And it should go down as you explain cluster differences with cluster predictors. It will go up as you explain level 1 variance with people predictors because they're yoked together. So anytime you reduce level 1 variance, level 2 random intercept variance is going to go up a little bit at least. The extent of that is due to how many people you have in your clusters. What else? What am I forgetting? I think those are the main things.
In a spot, it's a U.
It's a U, like just a regular.
Regular U.
Okay, well,
Capital, regular capital U.
then that's probably where I got it from. Like I'm not creative
I'm not
enough to
saying
come up
it's-
with my own.
I found a spot.
Well, I sometimes see the U that is in, is it upsilon, the Greek letter? That one looks like mu to me, and so I didn't want to do that one because I didn't want to confuse folks. Upsilon? Upsilon?
I think
Judges
it's
ruling?
upsilon.
Yeah, I don't know.
Is the E, I think.
Is what?
Epsilon is the E.
No, there's upsilon. There's a U version, right?
Yeah.
Yeah, one of these years I should learn the Greek alphabet. You'd think I'd know it by now, but I only know the ones that I've used before. We started looking at level 2 stuff. Design effects. What's a design effect? We forgot that one.
It's when you adjust for the effective sample size, right?
Yeah, it's how you create an effective sample size. It's the amount of adjustment needed to your total sample size that incorporates dependency. So it's based on ICC1 and the number of people per cluster. So that creates essentially a penalty factor that is the denominator. So you have total observations divided by design effect gets you effective sample size. And that's because to the extent that people have correlated responses in the same cluster, you don't have as much independent information from those people as you would as if they weren't from the same cluster. So that's an adjustment to the expected sampling. So we had a couple examples of that. This is something you might report descriptively in a manuscript. The way I see it used is just in sample size planning. So the end result is that, let's say, if you know that your power analysis said you need 225 people, for instance, and the only way you can get that many people is by sampling them in clusters, then you really need to get 500 people to get the amount of information that would be in 225. That's what this is telling us. So only when the ICC is exactly 0 would there be no design effect, and there's no penalty function. Yeah. Random intercept confidence interval, we did that one too. What's this tell us? Or do we want to start going back over this? Go back over? Okay, yep. Review or re-go over?
Re-go over.
Re-go over. Okay, I like how you said that definitively, right? Yes, I have an opinion. Excellent. Let's do that. This is slide 18. And I'll make sure I'm still recording just in case everything looks hunky-dory there. Excellent. So this is not a typical confidence interval. Let me contrast two of them. So here's a solution. This is SAS output, but I'll show you how to do this in Stata and R as well. These fixed intercept. So remember, when we have terms, we can't just say like the intercept or the slope. It's fixed intercept or random intercept. We got to be more specific. So 41 is the point estimate, as it would be called, for the fixed intercept. And this is the mean of the cluster means in this outcome, which I think is language. Yeah, language in a set of children nested in schools. The random intercept variance around that 41 is 17.8 with a residual variance of 62 that we don't need to pay attention to for right now. So a traditional confidence interval tells you the precision of the point estimate. The definition of a standard error for a fixed effect is the expected amount of deviation on average of any one sample from the population version of what it's supposed to be. So the expected wiggliness across samples I would accept, or inconsistency broadly construed, because if you repeat the same study, you're not going to get the exact same estimate back. So this is trying to give you a sense as to how wiggly it is. So if I use this standard error right here in a typical confidence interval, I have the fixed intercept plus or minus the range given by the amount of confidence I want from the z distribution, so 1.96 here, times the standard error. So this tells me an interval that I can expect the means to fluctuate in across samples, essentially. 95% of the samples are going to have the population mean between yay and yay. A random intercept confidence interval is a way of expressing how variable the clusters are expected to be from each other. So cluster mean differences are 22% of these data, right? What does that mean in practice? A random effect confidence interval is a way to try and express that in the metric of the outcome. So in this case, we start with the same center, 41.08, but rather than using the standard error of the fixed intercept, we are using the standard deviation of the random intercepts. So the square root of a variance is a standard deviation, right? So essentially what I'm doing is building a bell curve around the fixed intercept of plus or minus 2 standard deviations. And that's 95% of my clusters are expected to fall in that range for their means. So now I can say to the superintendent, 26% or 22% of the variance in language has to do with what school you go to. Like, what does that mean? Oh, well, the expected variation across schools in mean language is anywhere from about 33 to 50. That's a lot of variation. I think the scale of this goes up to maybe a score of 70 or 80, something like that. So it's
That's a big chunk.
a big chunk of the distribution. So I like this as a descriptive thing for folks. You can also, once we get to random slopes, we will do this for that as well. So then we can talk about what the range of the slopes is across clusters. So for instance, let's say that we have a gap due to free and reduced lunch. That's going to be one of our examples. Is the size of the gap the same, or does it depend on what school you go to? What is the expected range of those gaps due to free and reduced lunch? That's what a random slope confidence interval will tell us in about a month or so. Maybe not quite. 3 weeks, give or take. Okay, how does that sit with us?
Better than Upsilon. It is like almost a Y-ish, but it's like a cross between a Y and a V.
Oh,
That's an uppercase. Lowercase is actually a U-ish kind
yeah,
of shape.
that's the one.
So it's got both.
Yeah, I'll just stick with you. It's fine at this point. And we were, at the end, we're talking about relative model fit, I think. So here's the good news. Most of you have done this before, this process that we're going to go over. A likelihood ratio test is what we're talking about. The change in model log likelihood after adding parameters. If you had to sum up log likelihood in one word, what would it be? For some of you, this might be new, but for others, we talked about this in generalized. You would have talked about it potentially in other classes as well. Log likelihood in one word.
Model fit,
That's 2 words. I'll take it.
height,
Height, that was the word I wanted. Yeah. Literally, if you think about a likelihood function, like the normal distribution, for instance, has one. You put in the value of y, and you put in the model parameters, and out comes a number from that formula. That's likelihood. And under the idea that each person is independent, rather than multiplying all the likelihoods together, we take the log of it so we can add them together instead. And so then we say, given the model, how tall is this person's data under this distribution? And the way that the model estimates the parameters is to pick those that collectively make the data for the sample the tallest. So log likelihood is used to not only figure out what the best versions of the parameters are, but also to compare models. So if we add new terms to the model, we should make our data taller. It can't get shorter. You can't make it worse. The worst that can happen is it's not better in terms of that. So log likelihood is the unit that it starts with. It's an index of model fit in the sense of height collectively of the data. Now in our kinds of samples, people are not independent, right? That's the whole point of the class, dependency and all that. Mhm. So the standard likelihood formula, assuming a normal distribution, has to be altered to a multivariate normal formula. And it's the height of the cluster is what goes into the form and is added together. So the people within the cluster are thought of as multivariate observations. Repeated measures of the cluster is essentially how it works. And the same would be true in longitudinal data. Repeated observations for a person would form a multivariate height instead. I think I have more slides on that later on, but that's just sort of like the big picture overview. If you hang on to the idea of height, where bigger is better for log likelihood, that means that if we multiply it by -2, smaller is better. And the reason that folks do that is because the difference between log likelihoods times -2 is supposed to be distributed as a chi-square. And because folks know that you have to do that -2 multiplication, some software packages just give it to you directly. So for instance, -2 log likelihood for SAS and SPSS is what you get out of the mixed package. It sometimes comes out of R, sometimes not, depending on which version. So if you get -2 log likelihood, you're watching for it to go down to indicate a better model. If you get regular log likelihood, you're watching for it to go up instead. So you just got to kind of keep an eye on that. Stata users, I found a little function to print what the -2 log likelihood is. So even though on the output it only gives you log likelihood, there's a little piece of code I'll give you to get that, so you don't have to do the math. Yeah. So fewer minus more is always the order. The log likelihood for the model with fewer parameters minus that for the more, 10 times -2. Then we compute how many new parameters we have and compare that to a chi-square distribution. So this is something that is built into all the software. I had to write a little routine for it in SAS, but it's not that hard. So we will use this to judge improvements to the model with respect to the random effects, and random effects only in this class, because we are using a different kind of maximum likelihood estimation than what you would have used with likelihood ratio tests in other modeling contexts. I have a side note about this. This is something I want you to be aware of, but I just can't bring myself to care about. I just can't. If you use the number of parameters as the degrees of freedom when testing new random effect variances, you're going to be a little bit conservative. Just a little bit. That's because variances can't be negative. So in terms of thinking about a sampling distribution of what a variance could be, if your null hypothesis is 0, that kind of doesn't make sense because there can't be anything on the negative side.
Mm-hmm.
So it's not a full degree of freedom, essentially, because you're ruling out half the time when it would not have happened. Like you can't have a negative variance. So the solution to that is if you're only testing one thing, like one random intercept variance versus none, you can just cut the p-value in half. It's essentially like a one-tailed test because you only have one tail that you can possibly be. Cool. So that means instead of a critical value of 3.84, your critical value would be 2.71. And this is why I can't bring myself to care. Like, so infrequently would it be in between the two where you'd have to pay attention to this. If you're adding a random slope variance, you would use a mixture degrees of freedom 1 and 2. And that changes your critical value at an alpha of 0.05 from 5.99 to 5.14. And the further out you get, the less like it matters. Also, the more parameters you have, the more this little formula breaks down. So it can become an issue. There's an article on your reading list. I think that the last name is Stoll on that one, 2006 or so, if you're interested in these details. But otherwise, just know that if you use a standard chi-square process, it's going to be a little bit conservative. And I can live with that. Hopefully you guys can too. All right, so we talked about this at the very end. What can happen in terms of these likelihood ratio tests, or difference in -2 log likelihood. That's how you will see this abbreviated as well. If you're adding parameters, your model can get better or not better. So a significant test statistic would indicate better fitting model. If you remove parameters, your model can get worse or not worse. We're not going to have a lot of that this semester, but it does show up in other contexts. In addition, some folks like to look at something called information criteria, which are, both of these have -2 log likelihood as their base, and then they add a penalty factor for model complexity. So the traditional AIC, Akaike, I think someone once said. Can I get a judge's ruling? Anyone? Okay, I'm going with that. Is 2 times the number of parameters. BIC, or the Bayesian Information Criteria, is the log of sample size times the number of parameters. And you can imagine there's some ambiguity in what this means. Is it level 2 sample size? Yes, it is if you're looking at SAS. Is it level 1 sample size? Yes, it is if you're looking at Stata. And so this is, and also what is number of parameters varies across packages too. In standard maximum likelihood, all parameters count. In the version of maximum likelihood that we're going to use called residual or restricted, only the parameters from the variance model should count, but that varies across packages. So I've stopped printing these things in most of my examples because they're going to disagree. But know that inside a package, it would be internally consistent, where you want these values to be smaller is better because they both start with the shortness version of log likelihood, -2 log likelihood instead. So this is additional information that you may see supporting the choice of the model. So what would it be in this example with our language data? So the first example of a likelihood ratio test is something that actually SAS does for you, Stata does for you, R does not do for you. You have to ask for it, but I'll show you how to do that. Is whether or not we need a random intercept. So just for the empty model, do we need both levels, or is one level sufficient? Yeah, that's the question. So without the random intercept, so -2 res log likelihood, that means residual or restricted, take your pick, is this number right here. And if you're looking at this number going, is that good? Like, is a value of 25,000 good? The correct answer to that is, because these numbers are in the scale of the outcome. So there's no interpretation that can be made in isolation. These numbers only have relative comparison information in them. So it's the difference between models that we're going to pay attention to. And in this case, it's a difference of 451. So the model got taller by half of that. So the critical value for a single degree of freedom would be 3.84. Using the mixture is 2.71. So yeah, 451 is significantly high. In other words, using the model with the random intercept fits better. The data got taller. Said differently, our intraclass correlation that is created by that random intercept variance being added to the model of 0.22, that is better than 0, higher than 0. So that's putting it all together. An intraclass correlation is an effect size for how much of your outcome variability is due to which cluster you're from. The likelihood ratio test of the contribution of the random intercept is the corresponding significance test that goes with it. So if reviewer 2 says, do you really need a multi-level model? This is your answer. Yes, p less than 0.000001. Res log likelihood. Okay, I thought that was coming next. Good. It's like I made the slides. That's a joke. I think I've told it in some classes. I once got asked to give a pro seminar at Nebraska in another department. And after I was finished, one of the faculty in that department said, that was really good. It's like you knew it was on the next slide. And I thought to myself, well, I made the slides. That's kind of a low bar to know what I put in my own talk. Like, yeah, I had intent. I suspected I remembered my intent, if not the exact order of things. But like, this should be in here soon. So, all right, how are we doing? Thumb check. Water check. Okay, folks who are feeling a little sideways as opposed to vertical, anything we want to talk about, or I can tell you again. Yeah.
So I wonder, before we, like you said, before we decide if we need a multi-level modeling, should we always run this to compare like the model fit, see if we add a random intercept would be better?
In my examples, I'm going to show you to do that. I think in practice, no. unless it's somehow like a really weak signal, like your interclass correlation is 0.03 or something, and you feel like you need a p-value to back that up, I would say in most cases, like based on just the sampling design, your model should reflect that regardless of like what happens. So I would err on the side of, yes, it always needs to be a multi-level model. But, so when we get to level 1 predictors, for instance, I will show you how to put them in at level 1 and level 2 for the same reasons we need a multi-level model for the outcome in the first place, is because the predictors have both kinds of variance, just like the outcome has both kinds of variance. I've had reviewers push back on that and say that, oh, that's unnecessary, or these are too highly correlated. And so showing a significance test for the ICC of a predictor helps support an argument that, yeah, this predictor needs to go in at level 2 and level 1.
So usually multi-level modeling is always better. Usually.
Yes. You would, like, if you have a very small cluster size, then this test is going to be underpowered. So you have a harder time showing significance if you only have 10 clusters than if you have 100. And the variance that you get back across 10 is going to be a lot more inconsistent across samples than a variance you would get for 100. But there's nothing you can do about that unless you can go out and get 100 clusters. Yeah. Okay. Other questions, thoughts? All right, TAs, what am I forgetting? Anything you want to add?
Not yet.
Not yet? Okay, fair enough. So what complicates model comparisons is that only some are allowed. This is a distinction you have not heard about yet because it's only relevant in multi-level models. There are 2 flavors of what we call maximum likelihood. Maximum likelihood regular flavor and restricted flavor. Regular flavor maximum likelihood is also known as full information maximum likelihood. But the trick is, so is residual. Residual maximum likelihood is also a full information estimator. So this is a stupid name, is what I'm trying to say. FIML is used in the case of missing data. Like people say, I had missing data and I handled it with FIML. But you could also handle it with REML, because REML should actually be FIRML too. The word full information, what that means is it uses all of the original individual specific information in estimating the model parameters. That's what full information means. That's the default in almost everything nowadays. Back when these models were first being invented in the 70s and 80s, like it was computationally, that was a lot. So they didn't do it that way. That is in contrast with what's known as limited information estimation, which means you start with a summary of the data, and then your model is estimated using that summary. So as an example, if you've taken path analysis or structural equation modeling, you may have learned that all you need to reanalyze someone's data is their covariance matrix. If they print that in their article, or if they give you the correlations and the variances of the variables, that you can feed that information into a software program and you can analyze their data. That is a limited information approach to estimation. Missing data would create problems in that, but otherwise it would work. So both of these things use all the original data. Also, REML estimation is the same thing as ordinary least squares for these models. So if I used any of these mixed algorithms that we're going to use this semester for multi-level models to run a standard regression model, I would get the same information. It's the same thing. REML just allows you to have more complex models because you don't have to have complete data, normally distributed outcomes, and whatever level of independence. So in REML, the easiest way I can explain the difference between these two things boils down to sample versus population versions of the formula for variance. Do you remember this from like 1 million years ago?
Degrees of freedom.
Yeah. So I have ypc minus y hat here, meaning this is going to be form the residual for y, square it to avoid the negatives and positives canceling, sum it all up, divide by n minus k. K here is the number of fixed effects. So if you go all the way back to computing mean and variance, the formula for a sample variance was n minus 1, because in order to compute the variance in that sample, I had to know what the mean was. The population version, as shown down here, is just n. So n minus k is REML, and n is ML. That's the difference. In the likelihood function for these things, there's an extra piece in the REML version that adds back in the uncertainty that comes from having to estimate the fixed effects simultaneously. So it's like accounting for that extra step that ML doesn't. So why does this distinction matter? It matters in terms of which one you should use, and then therefore which model comparisons are valid. So I have this presented in a couple different tables. You can take your pick as to which one is more useful to you, but here's my best shot. So in estimating variances, and we're talking about random effect variances specifically, it treats the fixed effects as known if you're using ML. So that n, besides, not n minus k. So the uncertainty is not factored in, but whereas it is in REML. That means that in small level 2 samples, the random effect variances are going to be downwardly biased. They're going to be too small in ML. Less so the more level 2 units you get, after about 100 or ish, but it depends on the complexity of the model. Whereas in REML, they will be correct. So I would pick correct over downwardly biased. In these models, what do you think can happen if the variances you come up with are too small? Downwardly biased means too small. In other words, the model thinks we have less variance across clusters than what there actually is. What do you think?
You might not find significant findings. You don't have enough variance.
It's actually going to go, well, okay, yes, at level 2. That is true at level 2. Essentially, you have less variance to be explained at level 2. But at level 1, it's going to have the opposite impact because you're not introducing as much variance due to dependency as you need, which means the standard errors for the things at level 1 are going to be too small, which means their p-values are going to be too small. So you end up with higher type 1 error rates if you don't have enough variance at level 2. So I will be using REML whenever possible. That is the default in all of these software packages. However, REML is only a thing in models with conditionally normal level 1 residuals. That's it. There is no REML in generalized models. There's no REML in IRT. There's no REML in SEM. There's no REML in factor analysis. There could be, but there's just not. Yeah.
So can we say as long as we can use REML, don't use ML?
Yeah, that's what I would say. At some point, it stops mattering, but until you hit that point,
Yeah, this morning I was running something on SAS. I used ML, it's not working, but I changed to REML, it works.
interesting.
Yeah.
Okay, well, I haven't seen that happen very much before, but I suppose it could. Yeah. So here's the tricky part, though. We're all going to use REML no matter what. So now we have to pay attention to this rule. In terms of what can and can't be compared using -2 log likelihood, AIC, and BIC. Under REML, only models with the same fixed effects can be compared that way because it's discounting the fixed effects in its estimation. Essentially, it's optimizing the likelihood of the residuals specifically, and residuals depend on what they're residualized from as the fixed effects. So the REML likelihoods are on different scales if you have different fixed effects in your models. In ML, it does both at the same time, so you can do any kind of model comparison you want. So that's why up to this point you've never heard this distinction, because if you're using regular flavor ML, you can do any kind of model comparison that's nested. But we can only do it for random effects. So this is what we're going to do. If we're testing new fixed effects in the model for the means, this box right here, meaning I add a fixed slope of a level 2 predictor, I add a fixed slope of a level 1 predictor, we're not doing model comparisons. We don't need to. We're just going to look at the wall test that shows up on the output. Estimate divided by standard error is a t. Compare that. You get your p-value from that. You could use ML and do likelihood ratio tests, but not REML. You don't need to do it that way, but you could. If we are comparing random effects, we are not going to use any kind of wall test p-value because those are based on the idea of a two-sided sampling distribution for a variance that can't go negative. we are going to do minus 2 log likelihood, and then REML would be the better way to do it if possible. And if you want to do a model comparison that involves changes to both the fixed effects and the random effects, that has to be done in maximum likelihood. For non-nested models, there's really no significance tests. You would not be able to compare non-nested models unless you switched over to ML. If they differed in fixed effects, you could do so if they differed in random effects only, and you'd have to switch over to ML for that as well. So what we're going to do is sort of a different process in adding terms to a model, depending on which side we're adding them to. If we add fixed effects, we stare at the p-values that show up. If we add random effects, we do a likelihood ratio test. That's it. So the one way to screw this up, if I want to present it from that angle instead, what is the one way to get this wrong?
Look at the wrong thing at the wrong time.
Look at the wrong thing at the wrong time. It is refer to minus 2 log likelihood when using REML to talk about fixed effects. That's the wrong one. Everything else is some shade of okay. Also, all of these things are sample specific. So note the 30-point bold font up here. All observations must be the same across models. So what is going to happen as you add predictors is if those predictors have missing values for any of your cases, what happens to them? Bye-bye. All rows have to be complete. So if you add in a predictor and it ends up dropping a bunch of rows, your log likelihood will change for that reason alone, because it's literally the sum across observations. If you have fewer observations, that's a different total. So we want to be careful making sure that the sample size stays constant in the exact same set of cases if you want to do any kind of comparisons involving minus 2 log likelihood as height, or AIC or BAC.
So if you're going to do any kind of hierarchical work, you need to pretend you're at the end game and then go back to the beginning and work your way up. Otherwise, you'd have invalid comparisons if you lose data along the way.
Yes, if you're intending to do a sequential or hierarchical analysis where you add things in steps, that kind of deal, yeah, you have to be omniscient, know what you're going to end up with, and then pre-select your sample to be complete on those cases.
Okay.
Obviously not ideal in practice. If you don't have a lot of missing data, like less than 5%-ish is a heuristic I've heard, that's probably fine, but if you have more than that, you probably want to deal with it in a better way. The easiest way that I know how is to pretend a predictor is an outcome and bring it into the likelihood by estimating these models in multivariate software. That's the easiest way I know of. But that requires you being willing to say that the predictor is either normally distributed or to have software that anticipates it not being that. That's the tricky part. That's a whole nother class, right? Several of you took that. That's a whole nother class. Don't have missing data, especially for multi-level models, is the answer. But be prepared for your sample size to change. So in that case, like if I'm primarily interested in fixed effects, I'm not using minus 2 log likelihood to deceive, I'm just watching sort of p-values. And so I might do some stuff and just let the sample size wiggle around as I sort of sort things out. Where you can get into trouble, though, is like in this sample, this predictor was significant, but then in this subsample, it's not anymore. And it's like, oh, now what? That's where it gets a little tricky. Okay. Oh, new topic. Okay, any questions on this? Do you want to see empty models in an example before we do predictors? That good? How about that? Yeah, I'll switch over to example 2. So this is the PDF, just to make sure we know where to look for stuff. So each unit from this point forward will have a set of lecture slides, and then this handout that we're going to go through together. All of the original source files that built this handout, all datasets, syntax, output, and sometimes spreadsheets that I use for calculations or plots, will be in the zip folder that goes with this. So for instance, homework 1, due in a couple of weeks, will be based on the example we're about to go over. When you do homework 1, I would download these original source files. That way you can copy the syntax out of them directly. Students have sometimes encountered problems taking things out of the PDFs, like sometimes it adds weird characters and stuff when you try to copy text. So just use the original source files. And honestly, my examples are such that about 5 to 6 find and replace commands will usually get you through the whole thing. Am I right? Find and replace is your friend. Look for the patterns, and then that way you can start to build more efficient code. And then find and replace eventually can be replaced by functions if you know what you're doing. That's where I'm at. I'm starting to build little functions in R. It's very exciting for me. So. They're like, really? Like, no. It cleans up the code. It's nice. But anywho, these are data from a paper that is on your reading list, High School and Beyond. It's a data set that's been beat to death in a bunch of different multi-level modeling textbooks and examples, so I thought, why not join in that fun? I don't have a lot of cluster data in my possession. I really don't. I have a lot more longitudinal data, so I know cluster data can be a little bit harder to come by. But in this data set, it's very big. We have over 7,000 students from 160 schools, an average of about 45 students per school. We're going to be examining the extent to which student-level math can be predicted from school-level variables of school size and public versus private. So where this handout is headed is just level 2 predictors to start with. Level 1 predictors we will tackle in the next unit. So in this syntax, I try to show everything in terms of the code of both Stata and R, but then not necessarily have all the output in both. But for the first example of a model, I'll try to do both. But if you don't have the output for your program of choice, I refer you back to the source files. They have everything in those, so you can follow along in those if you wish. So steps in terms of data prep, this is Stata first here, setting where the stuff is, importing the Excel file. This is the step of filtering to make sure the data are complete with respect to everything that's eventually going to be in the model. So this is me omnisciently saying, I know what my final model is going to look like, therefore my sample needs to be this. I also wanted to generate the number of students per school so we could get a sense as to how variable that was. In Stata, gen means make a new variable, andegen is like a fancy version of a new variable using some kind of function. I don't know what the E means, but fancy is what I come up with. So in this case, I am building a new variable in that data set called n per school ID by counting the number of math scores by each unit of school ID. So it's just going to add that. I am then generating 2 sets of descriptive statistics for my level 2 variables for pedagogical purposes. So in the first version of this, I am essentially taking my level 1 data set and squishing it into a level 2 data set. I am taking the average across all the students from that school, putting that as one row, and Stata is doing this for me. But since I know I'm going to want to go back to my original level 1 data set, this process starts with the word preserve, meaning like, hey, don't dump that, like save it somewhere in your memory. Collapse this, all of these variables by school ID, so they're essentially taking the mean. These will be constants because these are level 2 school variables, as this one. Math is a student level thing, so it's going to take the average math across the students in that school. Summarize gives me descriptive statistics, and then restore puts me back to the original level 1 data set. So 160 schools, mean number of students is about 45, like I said, but it varies between 14 and 67, so quite a bit. Math ranges from, in this data set, we have an average of about 12.6, ranges from 4 to 19, so those are cluster averages in this level 2 data set, school averages in this context. Now what if I didn't go to the trouble and I just summarized the original level 1 data set? So that's the 7,185 observations. Note that the numbers are close but not the same. So for instance, the mean of math, that's the mean of the cluster means. That's 12.6. This is just the mean, 12.7. So they're going to wiggle a little bit in differently weighted data. Also, something like size. That is the number of students per school in the 1 row per school data set. That number, the school size, would be a constant across all the rows of a student. So if we don't aggregate up to the school level and just print descriptives for size, now the average size is 1056.
It's a weighted mean.
This is an unweighted mean and this is a weighted mean, essentially.
Oh.
So you can see where you might get different answers for level 2 predictors if the analysis doesn't understand that they're level 2 predictors. So I'm going to use school size in an analysis. However, before doing so, I'm going to rescale. So in the original version of this variable, what's a unit? Like a slope is the change in y per unit change in x. What's a unit?
The student?
A student, right? So the slope for school size would tell me the expected change in math per additional student the school has. Do you think that's going to be a big number or a small number? It's a very small number. So for variable predictors that are scaled very large like this, like if you have annual income in dollars, or the number of people that have this characteristic in a country, things like that. If your unit is going to be a very tiny thing, you want to rescale. So given this scale, the fact that there's 100 students at a minimum, and all the way up to 2,713, I decided to change it so that it is per 100 students, where the reference school would be a school that has 100. All right, here's the corresponding R code to do all of that. And as I said before, if you know how to import data and make new variables and do basic stuff like that in R a different way, Godspeed. There's a million different ways to do it. My code is meant to be transparent, not necessarily efficient. And it's meant to use base R whenever humanly possible. Do not ask me about the tidyverse. I'm content with being messy. So I'm going to set my working directory. I'm going to read in the Excel file. I've noticed sometimes when I import data that it's not a data frame, it's some other thing and I don't know why. So I just always do this, just superstitiously, to make sure that it's a data frame. I'm filtering to complete cases here, so only data that have all three of those variables. There is a function that Jonathan created that I stole. It is called addUnitMeans, and it does exactly what you would think based on that label. So I am taking the variable for student math. I am going to give it a new name of clustermean_math. That's what CM is going to stand for in this example. And it is going to append the cluster mean of math to the data set for me. That way I can look at the variance across clusters in the observed data. So example 2 is where the function is going to return this stuff, and it's coming from the same place. When students have tried to put it into a different data set, the function breaks. So just put it back into the same one. All right. So I'm now creating a level 2 data set to do descriptive statistics on, just like I did in Stata. There's a function called unique that allows us to do that. I'm using the psych package and the describe function then to get the descriptive statistics per school, which would be the same information we got up here, so no output files, and then the same thing for that as well, and then rescaling school size. All right. First step, unless there's questions about the data set or the story, we're predicting math, students in schools. Good? Good. All right, it's 1:26. Can we hang in there for a little bit? Yes, we can. I don't want to, but I'm contractually obligated to be here. Right?
So last class you said in this class it's better to not have missing data. But if we do have missing data, if we put it in when we run analyzing wrong, any difference for the results, or it's not working?
What will happen is that any rows that are incomplete get kicked out. That will happen whether you want it to or not. So what I'm doing here as a demonstration is, prior to including the predictors that I eventually want to have, I am ensuring that all rows are complete with respect to those. Because otherwise my empty model is potentially based on a different sample than where I'm headed.
Got it. Yeah. But in reality, if we are missing data, just kick it out.
It will kick it out for you.
Okay.
So yeah, that's the question of, do you want your sample to wiggle across versions of the model, or do you want to keep it fixed? And if you wanted to keep it fixed, which is simpler and easier to explain, then you got to kick out the missing rows ahead of time before the software does it for you.
Or if we have a small sample size, we may want to keep
That's right. If you're really worried about sample size or you have a lot of missing data and that's just not feasible, then you may have to live with a different sample for each model. But then that would complicate likelihood comparisons. However, in the use that we're going to do, it's generally to test random effects only. So if you put in a fixed effect, that fixed effect would have already kicked out all the cases that didn't have that predictor. Then you add a random effect, it would be the same model, like the same cases between those two models in particular. It's when you add new predictors that you're potentially going to drop rows. Cool. Other questions? All right. Then let's look at the simplest model ever. Single level empty means, no random intercept, so 2 parameters. First up, Stata, then R. So we're using mixed in Stata. The first word after mixed is your outcome variable. The space after that means I have no predictors. That's what empty means. Commas are used to separate things. And the rest of this you just have to sort of memorize. It's not obvious what you're asking for. But bar school ID is saying I would like a random intercept, and this is my level 2 ID variable, please. Random intercept is the default. Then after that comma, these are all options. So no constant means I would actually not like the random intercept that's default, thank you. I would like REML instead of EML. I would like to use degrees of freedom because base data does not by default. And I would like you to use, put the p-values in the table with it, and no log means don't print all the iteration history in the output to sort of clean it up a little bit. So this is a standard single level regression model with just a fixed intercept. That's what this is. So the mean across all the students, unweighted, is the 12.7. That's what we saw just a minute ago. And then the variance across all the students in all the schools without paying attention to clustering is 47.3. So that's my variance of the e's from this model. Stata gives you log likelihood as your index of model fit. So then what this little command does right here, ELL times -2, that is a piece of output that has been saved internally in Stata, and I'm just asking it to print it. So if you're doing your homework in Stata this semester, the first question for any model in it is going to be what is the -2 log likelihood? This would be the number that you input instead of that one. The reason that I ask you for -2 log likelihood is that it is functionally a thumbprint for you to know whether you have the right model in terms of the outcome and the predictors. It's a unique identifier. The next question will often be what is the fixed intercept? Because that tells me if you have the right centering or coding scheme for your predictors in terms of what 0 means. Because the fixed intercept is the expected outcome when all predictors are 0. If you get that wrong, what 0 means is off somewhere in your predictor list. So the questions in homework are designed to make sure you're on the right track and sort of to dial down in terms of the level of specificity. But this one will tell you if you have the right model to start with. In single level regression models, I use residual variance as the analog to this because it does the same thing. All right, in R, I wish there was just one function in R that did all the things. There is not. I wish there was one package in R that did all the things. There is not. So you're going to see a little bit of variety this semester in terms of what these things do. This one, because I did not want to have a random intercept, I am using a function called GLS, stands for Generalized Least Squares, from the NLME package. This is used for models with conditionally normal residuals, both univariate and multivariate. So I've done a multivariate analyses with this function as well. Does it use for anything else you're familiar with? You were nodding. You've seen it before? Or you just like GLS?
No, I've seen it before, I just don't remember.
Don't remember?
When was it?
Fair enough. Well, this one is what I need if there's no random effects, because all the other functions insist on having those and won't let you take them out. I am asking it to show -2 log likelihood, because it doesn't do that by default. And then, of course, I want a summary of what the model is. So I'm naming these model 0 to start with. So the first thing that it prints then, based on the order in which I requested it, this is -2 log likelihood. So this is what you would enter in your homework if you're using R. Yes, sir.
Quick question, Lisa. If you are meeting the random intercept, why you are not using the LM function to fit a linear model, the traditional linear regression?
Good question. The reason is because I wanted to do a likelihood ratio test, I think, but that's another option. This one also, if I, for whatever reason, if I wanted to do maximum likelihood instead, then I would need to use this function.
Great.
I think this one might have link functions in it somewhere. I could be wrong on that, so that might be another one. But yeah, LM could have been used as well.
Yeah, but you are right that with LM we have OLS by default.
OLS is RUML.
We
Yep.
couldn't perform the likelihood ratio test if you use ML to fit the random intercept model, right?
Yeah, I think when I'm using Renova though in the other thing.
Uh-huh.
Yeah, the answer is I could have done it that way. I bet I had a reason, and I'm not sure what it is anymore. You accept that? Okay. Yeah, Lisa 2 years ago decided on this, and you'd have to talk with her about what that decision process was like.
We'll phone a friend.
I don't know that I would have articulated it to anybody else either, so you're kind of on your own. All right, so then same answers here. We have, it spits out AIC, BIC, and then regular flavor log likelihood. So this value times -2 is how we get to that one. Intercept of 12.7, which is my overall mean. And it also tells me degrees of freedom. So in this case, it's not differentiating level 2 from level 1 yet. And for whatever reason, it doesn't print the residual variance. So I had to ask for that. It's buried as an object in there. So I found that, and there's my 47. Okay. So I would not normally do a single level model. I just wanted to show you sort of how the numbers matched the descriptive statistics because that's what's happening. And they will change after we add in random effects. So here's a 2-level model, your very first multi-level model. Aren't you excited? Well, not the very first for some of you. I know Dan had longitudinal, but it's the first for this fall. So we have our little notation here, math. Yay, math. Yeah, put your words in there whenever possible. Math is better than Y in terms of your reader's working memory. Math PC. What is this right here? And not quite. That's what I'm saying. It's
No, that
yeah.
that is
This is
that's your random interest. Well, no, it's not your random.
Yeah. Let's start here. What is this thing? Say it again.
Fix it.
That's my fixed effect. Specifically, what kind of effect? Starts with an I.
Interesting.
Yeah, intercept. Yeah, we have intercepts and slopes as fixed effects, just like we have intercepts and slopes as random effects. So we got to be a little more specific. So this is my fixed intercept.
Yes.
What is this?
Your random intercept based off a cluster.
Yeah, this would be the random intercept for cluster C. So this is representing the idea that we have this random intercept variance across clusters as one of the model parameters. But this right here is not a variance. This is a value for cluster C specifically. So if I put together the fixed intercept, which is the mean of the cluster means, and then I put together that with the random intercept, which is how far off that cluster's mean is, altogether I get what?
Intercept for cluster C.
Yeah, the mean or the intercept overall for cluster C. So this is cluster C's intercept, which is just a mean right here because we have no predictors. So I call this a placeholder in the sense that it doesn't have anything unique to it that isn't defined by the parameters that contribute to it. You can also think of it as a latent variable and a cluster individual outcome. So let's see what happens. So in Stata, all I did was remove the no constant to turn the random intercept variance
That's so
back on.
big, we can't see very much.
Hmm?
Or did you purposely zoom that much so we can see the whole?
I was zooming in on the equation.
Well,
but I should zoom back out for all
that's
the
why
words.
I wanted to.
Yep.
Yeah.
There we
Sorry.
go, unzoomed. That's better.
Cool, thank you.
So I'm saying like this is the change to the code. I took out the no constant to put the constant back in because Stata calls the intercept the constant. I know. I'm also switching my method of degrees of freedom. So degrees of freedom for the denominator in these models is hella complicated. There's not a single right answer. There's a bunch of different ways of doing it. The one that is, I'd say, the most commonly offered across packages and has been shown to work well in practice is something called Satterthwaite. Some dude made it in like 1946. His name was Satterthwaite. It is analogous to how degrees of freedom are corrected for a dependent samples t-test with different sample sizes and different variances. The ugly matrix equations are in documentation for SAS mixed. I pointed you to them, Vladimir, right? Did those help you at all?
Kind of.
Kind of. Okay, well,
But
better than you
can
than me.
find more information on Google. It's pretty interesting how all of these things work, specifically because this is related to how the standard errors of the fixed effects are calculated in linear mixed models.
Yeah, so Kenward Roger is another method that you'll hear. That's two dudes who worked together to make a new thing in like 1997 or something, so this is newer. They took Satterthwaite and then they also add a small sample correction for the estimated variances that somehow makes them less wrong. And that's the extent of my knowledge on that topic. Yes?
Can I ask you a question, Lisa?
Oh,
Because
no. Yeah.
related
You can
to
try.
the,
You can try, go ahead.
yeah, but it is related to the BOC because you said that that's like a latent variable, right? We
Mhm.
can interpret it in that way because
Yep.
we have a mean, we have a variance
Yep.
to identify that thing that we cannot observe. Although, is the UOC a random variable too, given that we assume that's a normal distributed thing with mean zero and estimated variance?
So BOC here would not be a variable unless you added in that part. So there is a variance of the U, and then we would add to that prediction this constant number, and that would create this. So I'm thinking of latent variable as this in the SEM version of it. Because like if you have a circle and it is being predicted by stuff, then like that the name of the circle would be that thing, and then all the stuff coming into it would create fixed and random effects. So this is the mean of the latent variable. This would indicate the deviation from the mean representing the idea of variance.
Got it, thank you.
Yeah, this is a distinction that like in my textbook, I focused on that part, but really it should be this part.
Awesome. Okay, got it. Thank you.
Yeah, so degrees of freedom, where we were at here. Essentially what's going to happen is that any term that has a random effect with it is going to have degrees of freedom that look more like level 2 sample size. Any term that does not have a random effect with it is going to have, if it's a level 1 predictor, look more like level 1 sample size, and if it's a level 2 predictor, look more like level 2. So the Satterthwaite degrees of freedom takes into account the sample size at each level and the amount of variance in the predictor and the outcome at each level as part of the math. Simulation studies said it worked good, okay? Just trust them, it's fine. So let's see here, just a couple minutes left and then we'll have to run through that again next time. So Stata helpfully spits out all kinds of stuff about your sample. So you would want to stop by here and make sure that this looks right in terms of how it's reading your data, that kind of thing. So I have my new mean is 12.6 instead of 12.7 because this is the mean of the means. This is a weighted mean, just like we saw from the level 2 data set. So this is gamma 0, 0. In terms of the variance components, it's not labeled super helpfully, but school ID identity varicants, that's your random intercept variance label. So 8.6 is the amount of variance in the U zeros across clusters. Var residual is going to be my level 1 variance. That's my E variance across people of 39. This down here, LR test versus linear model. That's what it is. So this is the test of the random intercept and whether you need it. The likelihood ratio test is done for you in this instance of empty models. And prob greater than or equal to chi-bar. That's a mixture chi-square. That's what that's referring to. So yeah, a test statistic of 986, I'll call that significant. What do you think the ICC is? You don't have to do the math in your head, just tell me the formula. What's the numerator? 8 or 39? Numerator for ICC 1, or 2 for that matter.
I think it's the
39.
8.
Yeah, it's the 8. And
Yeah.
the denominator would be 8 plus 39.
Yeah.
And I don't do math ever,
47, 8.
but Stata does.
It's about 16%.
18%.
Oh,
Very good.
sorry.
I know.
done.
SStat ICC. So SStat means give me something from the analysis you just ran, broadly construed. There's like just a list of, like, they're called post-estimation commands. Here's one. So here's the formula, here's the results. So yeah, how would I talk about this in words? 0.18 is what?
It's the percentage of variance associated with the cluster means?
Yeah, I would say it's proportion variance.
Sorry.
Yep, associated with the cluster mean differences. Or the average math score is correlated 0.18 from kids from the same school. And is 0.18 better than 0? How do I know that? I should say higher than 0, not better. I know that-
the likelihood test?
Yeah, that's the likelihood ratio test. So the model gets taller by a whole lot if we allow the random intercept variance. So
Now,
that's saying to allow a correlation of residuals from the same school makes the data taller. That's what
Now,
we're saying.
did you say based off of last time that that's actually pretty high?
It's very, very high.
I'm just trying to.
Yeah, like this interclass
That's all.
correlation for math is very high. I don't know if these data are real, quite frankly. I have my doubts, but
I don't care if it's real
I
data or
don't-
not.
yeah, not
I'm
really.
just trying to ballpark and trying to.
they did a decent job making it look pseudo-real though, so I'll give them credit for that. All right, you know what is not pseudo-real? It's time to go. You hung in there. Good work. 144. Any questions before we call it a weekend?
I had one, but it involves you scrolling up, and because I don't remember the question, but I know it had something.
Okay, should I just scroll slowly
Stop.
until it jogs your memory?
Yeah, stop right there. Yeah. Let's see. Why do we have three levels of degrees of freedom: the minimum, average, and max?
I don't know.
Okay.
I think at this point it's because
I mean,
there's
they're all
only
the
one.
same right now.
Yeah, because there's
which-
only one. So later, when there's more stuff in this table, there will be a range, and I think this is reporting just a summary of what those values ended up being,
And they happen to be all the same if they're all the
because
same
there's
value.
only one number. Yep.
Okay.
Okay, I do know. How about that?
You did know. Okay, thank you.
All right, I'll hang out for a few minutes if anyone wants to chat. Thanks for being here. Do your first formative assessment, please, and I hope to see everybody on Tuesday for Garbage Day. All right, peace out.